in this class, I'm just going to do linear regression in R, so you can all play with it. And it's largely experimental, and you can do much more with this by yourself. So I'll just give a couple of examples and then stop it. Right. So now I take a data set called Iris. So let's just check what Iris is. So Iris is Edgar Anderson's famous or Fisher's data set, where they went and measured sepal length, width, and petal length for 50 flowers, and they discussed this with 3 species of iris. So the species of iris are, I think, Setosa, versicolor, and virginica. And the data frame has 150 rows and 5 variables, and you can, let's just check them out. Let's go to head of iris. Let's go head of iris. Let's run that. So it has sepal length, width, petal length, petal width, and the species. That's the 5 rows, and it has about, I think, 150 data points among these 5 columns. So what we want to do is, I want to check if the sepal length has any relationship with regard to petal width. So let's write down. So let's say we want to check if sepal length is linearly related to petal width, right? Let's do that. Let's check that. So what I do is, R has this whole thing set up where you can just check LM is for linear models. You can use the function lm to check if this variable is related to the other variable, petal width, and you take the data set as iris. So let's run that. Let's cover it fit. So once I have fit1, then if I do summary of fit1, it gives me all the things. For example, let's go back. So summary of fit1 tells me, the first thing it does is it estimates the beta naught is 4.77, beta 1 is 0.8858, and it gives me the p values for t, and then it's quite small, so we can't reject the null hypothesis, which is beta 1 is equal to 0. So that means it's generally a linear relationship perhaps. And then it also gives you the smallest residual sum of squares and the largest one residuals, not squares, just the residuals, right? Very good. It also gives you the R squared statistic is 0.669. It's not quite close to 1, but it's not close to 0 as well. And the residual standard error is 0.478. Very cool. So, and then the F statistic we will discuss later on. We have not done that till now, but you can also use the F statistic, which I didn't discuss in that class in some sense. So now you can also check if by yourself. This perhaps the first thing you should do is plot it, which I didn't do. I'm sorry about that. And then you just fit a line. The app line is the L fit one line. So it's sort of it's believable that's a linear relationship. It's growing like this in some sense. You could also do a little bit better graph to the whole thing. The ggplot does it for you. It shows you the linear line as well with sort of an error band between for the slope. It also plots what I did, the confidence interval around beta naught hat and beta 1 hat. So that's the first part. So the first part is linear iris. The second thing I wanted to show you was that if you just wanted to code it yourself, right? Let's say I have the data set x1 is this, x2 is this, and I just create an artificial model that y is x1 plus x2 plus normal with mean 0 and standard deviation 0.3. So that's my data set. So if I look at y, it looks like some perturbed values of x1 plus x2. So my true model is beta 1 is 1, beta naught is 0, beta 1 is 1, beta 2 is 1 as well. And that's how the model looks like, right? So if I do my least squares, I should get it. Let's just check if that's the correct one. So y is this matrix, x is this matrix, right? Let's make it in the matrix. So I want to use the normal equations. So this is exactly, I'm just solving x transpose x beta x transpose y, I get beta hat is this. So now let's just check what beta hat we get. So it's not so bad. X1, X2 are close to 1, but I do get a negative slope intercept because of the way I've jigged the normal random variables, right? So that's okay. That's not a very bad thing. The model is doing quite well. That is, I am getting X1 close to 1 and X2 close to 1 as well. So now I can do the same thing with the R package, LM, and I look at the LM coefficients. I mean, they're also very exactly what I get as well, right? So it's like, so the same R does exactly normal equations. That's all I wanted to show you in this thing. So you can try, and a good exercise to do is you take artificial data sets. You can play with. So simple exercise you can try is change variance of the normal of R norm and see how the data perform, how the model performs. So if you have larger variance, just check if the model does well, or smaller variance, that's how the model does well. Cool. Very good. So maybe we can also try to plot it, but you can try to also plot it and check. Let's just try to plot the whole thing and check it. Very good. I just wanted to introduce you to a couple of things. One is there's a book called ISLR. It's a statistical learning book. It's available on the web. You can just go to the website and get this book. And that they have this code. So I just it requires two packages, MASS and ISLR, which is ISLR is a package that they have. So they consider a data set called Boston. So let's just look at what Boston is. Boston is a data set. I think it's suburbs of Boston is assessed for housing values. That's how good the housing prices there or what it will be. So what they go and do is they go and measure a variable called CRIM. It's a per capita crime rate per town by town. ZN is zone size, I guess, and so on and so forth. And then we'll focus on two things. One is that the median value of owner-occupied homes in $1,000 and the lower status of population percent. So where they are in the population. So if I do head Boston, that's what gives you, and name Boston gives you all the variables that are there in the data set. So suppose I want to just check how the median value of owner-occupied homes fits with the status in the population. I do this LLM fit. It should give you an error because I have not added the data set, right? And then similarly here, if I put data equal to Boston, then it will add the data set and give me the answer, right? Give me the answer. So if I do summary of LM fit at the bottom, if you see it, it should give me the answer. We'll come back to discuss the answer in a second. Another way to attach data set is to attach Boston first and then do this thing. Yeah. And if you do LM fit, it gives you all these. If you just do LM fit, it'll give you the intercept and the coefficient immediately. And summary of LM fit, you can just check, and then it'll tell you that okay, the p-value is small, the data set is quite good, the fit is quite good, and various things. R squared is not so high, but it's 0.5 and so on. And then you can also, this LM fit, you can also check how to grab variables from. If you do name to LM fit, it gives you all these things. You can grab it. So if you do coefficients only, it'll give you beta naught and beta 1 hat. Beta naught and beta 1 hat. And if you want the interval, it'll give you the interval as well. So it's 97.5% interval is around this time. So 33 to 35 is the interval for beta naught hat, and minus 1.03 to minus 0.37 is that. And in that package as well, they give you how to predict. You can use the LM data to predict a little far away. So let's say you want to predict at 5, 10, and 15, and you just can predict, it'll give you the answer. Right? Gives you the answer with the upper and lower bound intervals as well. The fit gives you 29, and the lower end is 29.00, and the upper end is 30. And similarly, you can do prediction as well. It'll do the same thing as well. And you can plot and check. It doesn't look quite linear, but it's okay, I guess. You can make it a little bigger. That's what they do, and then bring color red as well. Okay, I will stop with this. And then, okay, so I did some little bit more plotting. I guess it's nothing major. So I just put everything in red, and I just made it little different colors to show you how to do this. And then different shapes, and then so it's just you can plot everything in the one line. Let's just do that. So we plot. If you set up a chart area, this is quite good to do. Let me just do that for you. And then I'll stop for the day again. So if you just set the chart up and you do plot and fit, it gives you all the plots together. So these are 4 plots. One is residual versus fitted. The fitted values was the residuals. You can just check how they're quite small or large. It'll give you an idea what's going on. This is like a kind of a validation of the model in some sense. That is, see, we assume the model is y equal to x beta plus error is normal, right? Now, if the error is not normal, then the QQ plot should be quite bad. So here again, the QQ plot is sort of varying at the top, so indicates that the model itself may be in question in some sense. These two things are a little bit more advanced things. We will try to sort of come back to them at some point in time. And this okay, I'm doing the same thing again. Then plot the p hat values and look at which one's maximum. Okay, I'll stop.